All right, this is the last video on chemical kinetics, and so what we're going to focus on today is reaction mechanisms, and then we're also going to talk about catalysis or catalyst, both homogeneous and heterogeneous, and that should wrap up this chapter. So when we have a chemical reaction, I think a lot of people they think that reactions happen in one step, and they generally don't. They generally don't just go from reactants to products in one fell swoop. We can kind of see that before we saw the chlorine collide with the nitrosyl chloride, and then the bond breaks between the chlorine and the nitrosyl chloride, and then it reforms as a chlorine molecule. Those so it's multiple steps for an entire reaction usually, and so a balanced chemical equation for the most part is actually a summary of little individual steps. So that's what we're going to find out in this section, is that reactions generally don't happen in one fell swoop. It is a series of steps, and yes, we will get a balanced chemical equation out of it, but that balanced chemical equation doesn't illustrate how many steps it took to get to the products. So, for example, A reacts with B and forms C. That's one step. And then when C is formed, it reacts with B and it forms D. So what we see as the overall balanced chemical equation is A plus 2 moles of B form D, but that's not how it actually formed. It didn't happen in one process. It happened as two elementary processes. It happened as these two steps. So these are called elementary reactions, and this sequence of steps, the sum to give us the overall reaction, is called the reaction mechanism. So that's what we're focusing on this section, reaction mechanisms. Really important in biology, metallurgy, material science. These are the people who probably are going to focus on this section more. So, for example, we have seen this reaction before. We have 2 moles of nitric oxide, and it reacts with oxygen to form 2 moles of nitrogen dioxide or nitrous oxide. So, here we have NO, nitric oxide plus nitric oxide yields dinitrogen dioxide, dinitrogen dioxide. And then dinitrogen oxide reacts with oxygen to form 2 moles of nitrogen dioxide. So, what you notice is this dinitrogen dioxide, it wasn't present initially, and it gets consumed in the second step. And so that's called an intermediate. Wasn't present initially, and it's not in the final products. That is an intermediate. I want you to know that term. That's a term I will test on, at least on the quiz and your assignment. The intermediates appear in the mechanism, but do not appear in the final balanced chemical equation. So each one of the steps is called an elementary reaction. You've got to speak the language. So elementary reaction is the individual steps, and one that occurs in a single collision. All right, so keep that in mind. Molecularity of the elementary reaction is essentially the number of reactant molecules involved in the collision. You go, why do I need to know this? Because the real importance of this is that we're going to start seeing how this is related to the rate law that we've been talking about. So we have unimolecular collisions, we have bimolecular collisions, and termolecular collisions. So unimolecular is when only one molecule reacts. So that's like when A becomes B. And all that happens is A is flipping to B. That's going to be a unimolecular, one reactant molecule. Then we could have A collides with another A molecule, and that forms B. And that would be a bimolecular collision where two reactant molecules collide to form B. And then a term molecular is where we would have A plus another A plus another A all have to collide to form B. And you can see this is probably a really slow reaction. What's the chance of all three A's colliding at the same time in a certain orientation to form product B? So these are really slow. We don't see these as much in nature as the first two. This we've already seen. This is like first order reactions. First order reaction. A to the concentration of this reactant raised to the first. And then this is like a second order reaction. So that's why this is important. It's two A's colliding. And so we wrote this in the rate law as A, and we wrote this as A raised to the second power. And then again, rate law says we have to put a K in here, and then we got to put a rate here, overall rate. So that's what's so important about this, is that the rate law and the types of collisions are related. And that's what we see here. So elementary steps, we have A going to product. So the rate of that is the rate law. The rate law is rate equals K times A. Then we have A and B. And then notice this, the rate law is K times the two reactant concentrations in moles per liter, A and B. And that's going to be second order overall. So this is first order, the first one. And then second one is second order. So A colliding with A, we just saw this. This makes this second order in A. And it says, the preceding examples show that the reaction order for each reactant in an elementary reaction is equal to its stoichiometric coefficients. This is where students make the biggest mistake. They think that if you write 2 moles of H2 reacts with 1 mole of O2 equals H2O, or let's say yields H2O, that the rate law is going to be rate equals K times the hydrogen ion concentration raised to the second power and the oxygen concentration raised to the first power, because that's what the coefficients are. The only way these orders can be determined is experimentally. So we have to have a series of experiments to see what the relationship is between the concentration of hydrogen and the rate and the concentration of the oxygen and the rate. So when students write the rate law based off stoichiometry, it's incorrect unless it's an elementary reaction and it's equal to its stoichiometric coefficients. I can tell you this is not an elementary reaction. We can tell it's not because we know that in one step the bond has to break between the two hydrogens, and the bond has to break between the two oxygens, and the hydrogen has to collide with that monoatomic oxygen to bond with the oxygen, and another hydrogen has to collide to form H2O. So we know that this was originally not an elementary reaction. So do not use the stoichiometric coefficients to write the rate law unless it is an elementary step. And that's where I see most students make the biggest mistake. With reaction mechanism. That and the next one. There's another mistake a lot of students make. So we'll talk about that in a second. In general, it says we cannot tell just by looking at a balanced chemical equation whether the reaction occurs as a series of steps or in one step. We can't do that in general. But you can generally think about it like if you see something like H2 plus O2 yields water, that just looks too complex. I don't know, maybe it doesn't to you, but that looks too complex to me to be one step because there's a lot of bonds breaking and new bonds forming. All right, so this is the next thing, most important. If you get anything out of this chapter, we've talked about that the elementary step could be the stoichiometric one, but otherwise, if it's a series of elementary steps to make the overall step, then the rate law is not going to be just what the stoichiometry is for the overall reaction. So here's the big one right here. Rate determining step is the slowest step. whatever the slowest step of the elementary steps, whichever one is the slowest is going to determine the overall rate law. All right? So the slow step determines the overall rate law. You say, well, how am I supposed to use this? Well, here's the rules. The steps of a proposed mechanism must satisfy these two requirements. The sum of the elementary reactions must be the overall balanced equation for the reaction. So when you add up all the elementary steps, it has to equal the overall reaction that is balanced. And the rate determining step must have the same rate law as determined from the experimental data. All right? Make sure you know this one. The rate determining step, which is the slowest step, must have the same rate law as determined from the experimental data. And if it doesn't, you're not onto the right mechanism. So that's what people are doing that's trying to determine mechanisms. They have to follow those rules. All right? So let's look at this reaction. Would you say this, just looking at this, would you say this is an elementary step or would you say this is an overall reaction? Well, they tell you it's overall. But if just looking at it, I hope you don't say, oh yeah, that's an elementary step. There's no way it is. There's going to be bonds breaking between the oxygen and the hydrogen, and there's going to be some kind of hydrogen-oxygen formation. I mean, if you say these two oxygens just left like this, left like that, there's still got to be oxygen for this oxygen to be bound to the hydrogen. That is not an elementary step. You can tell it's not. It's too complex. All right, so then we find out experimentally, can't stress that enough, that the rate law for this reaction looks like so. And I don't know why there's a gap in here. This is all one compound. This is hydrogen peroxide, so a little typo there. And the other thing we see is we see iodine in the rate law, and you're going, we don't even see any iodine up here, right? It just says decomposition. Oh, yeah, it says decomposition with iodide ions. But iodine is not in the balanced chemical equation. So it does say that. There's iodide ions, and it enhances it facilitates the decomposition of the hydrogen peroxide. If you ever seen this reaction, it's really cool. You could maybe ask your professor to do this in the lab, but you just take some hydrogen peroxide. You might want to put some soap over top of it. And then you add some little bits of iodine, potassium iodide, or something like that solution. All of a sudden, this thing if it's in a graduated cylinder, all of a sudden it just starts bubbling up with foam, and it comes out the top. And that iodide has a part to play in it. All right, so that's where we're going with that. Neat reaction. So we propose, and that's what happens. We propose a reaction mechanism for this reaction. So what we're going to say, and this makes sense to me, you have hydrogen peroxide, and it collides with an iodide ion. And so when that collision happens, one of the oxygen bond breaks, and one of the oxygen bonds with the iodide ion. Okay, so that's step number one. Step number two is this hypoiodide ion, let's call it that, hypoiodide ion, then reacts with another hydrogen peroxide molecule, and that forms water, oxygen, and iodine. All right, so what we know right off the bat is this hypoiodide ion is a intermediate. It wasn't at the beginning of the reaction. It is not at the end of the reaction. It's an intermediate. All right, so then the rate of reaction can be determined from the first step alone. And the reason why is this must be, since the overall rate of the reaction is this, then this must be the slow step. And the slow step is the rate determining step. So because the rate law looks like this, we know that step number one must be the slow step. So again, the iodide ion does not appear in the overall equation, but it is consumed in the first step and produced in the second step. So let's go back to that. Let's see, do they show it on the... let's go back to the other slide just to show that. So notice the iodide is consumed here, but then it's reproduced here. So it's not consumed in the reaction. So the iodide ion is a catalyst. A catalyst, and its function is to speed up the rate of the reaction. So rate of reaction is molarity per second. So this reaction speeds up. So what you notice is if I just pour hydrogen peroxide in a tube and I put it in here and I put some soap on top, nothing usually happens. It's not till I add the iodide ion, all of a sudden it starts foaming up and coming over the top. So the iodide speeds up the reaction. It's not something that is consumed completely in the reaction. It is consumed, but then it's reproduced, and that's what a catalyst is. A catalyst is a substance that is not consumed in the course of the reaction, and it may either speed up or slow down the reaction. Oops. All right, so this is what, if we draw potential energy versus reaction progress. So as the reaction happens, here's our reactants. I want you to be able to interpret this plot. The first step, we go all the way up to this activated complex here, and that is E sub A for the first step. Notice it's a huge number. So we have to get enough energy to get up to the top of that peak there. And then once we get to the peak, we stop and we go down to here. So we go from activated complex, which we've talked about in the previous section, activated complex or transitional state, to forming an intermediate. That's this step here. Then the intermediate is consumed, and that gets us over the hump here to form the product. And the intermediate you don't see. So you don't see that IO negative at the beginning of the reaction or at the end of the reaction, but we had a place there where it was formed and it was consumed. And again, we have to get over this activation energy from this bottom to that line there. That's the activation energy for the second reaction. All right, so that's what it looks like. It's two steps. You've got step one where we form the IO negative, and then IO negative is consumed and we end up with the products. So be able to interpret the plot. All right, so then we can say that the proposed mechanism is plausible, not that it's necessarily correct. So this happens a lot. Just because the rate law matches an elementary step, we just say plausible. We don't say it's the truth, because we can't visually see what's happening in the reaction. So it's not possible to prove it is correct using data alone. Okay? So it says to determine whether or not a proposed reaction mechanism is actually correct, we must conduct other experiments. It's not easy. You can spend your whole life calculating or looking for true reaction mechanisms. So in the case of hydrogen peroxide decomposition, we might detect the presence of IO2 ions. So that intermediate, once it forms, if we can detect that, then we can say, hey, if we can detect them, then we can support our proposed mechanism. So that's something we would look for. And that's something you do as a chemist. You don't know what's going on in reaction, so you have your ideas, you write it down on paper, you expect this. Again, if you think this reaction mechanism was correct, then you suspect that this IO negative, let me check something there. Yeah, IO negative is present. All right. And so we would check for that. An intermediate. Yeah, there's a mistake here. This should be, yeah, that's what I was looking at. This should be IO negative, not IO subscript 2. All right, so similarly for the hydrogen iodide reaction, detection of iodine atoms would indicate the support of a proposed two-step mechanism. For example, it says I2 iodine diatomic dissociates into atoms when it's irradiated with visible light. So what they're saying here, dissociation, you got to speak the language. It dissociates into iodine, 2 moles of iodide, and that thus we would predict the formation of hydrogen iodide is from H2 and I2 would speed up as the intensity of light increases, because that would increase the concentration of the I atoms. All right, so let's see what happens here. Oops, they kind of dropped us off here. I thought they were going to show that actual reaction. So this reaction must be in your book. So I would recommend that you look at the reaction. The overall reaction would be H2 gas plus I2 gas yields 2 moles of HI. So look that up, and hopefully that'll help you with that one. I hope you are reading the book. I hope you are cracking it open, reading it, because, you know, these PowerPoints, they're like a tour guide. I mean, I'm showing you the parts. I'm talking about what's important. I'm stressing the definitions. I'm showing the calculation. But you need to read the book to see examples, multiple examples of how they go about it, so you can see the pattern. All right, so we have methyl acetate. We're going to react that with water. So that forms acetic acid and methanol. And so what happens here is there's a possibility of where the bond is broken. Could break like that, add a hydrogen to it, and it becomes methanol. Or it could break like this, and then we add an OH group to it, and it becomes methanol. So there's two possibilities for the reaction here. So how do we know? Well, we use an isotope of oxygen that is different than this oxygen, and we follow where this, what happens to this oxygen. All right, so that's how we're going to determine reaction mechanism. So it says, thus, the reaction might have occurred via bond breaking, scheme A, or because the product formed via scheme B, and would have retained both its original oxygen atoms and would contain no oxygen 18. So if both of these, if it's just this, then we can distinguish this oxygen from this one, because this is a different isotopic mass. This has got 2 more neutrons than this one. So this is what we use to determine what is the mechanism. All right, so let's look at this again. Let's look at identifying plausible reaction mechanisms. There's 2 criteria that must be met for the proposed mechanism. The individual steps, the elementary processes, must sum to the correct overall reaction, and the rate determining step, the slow step, must give the same rate law as the experimentally determined rate law. All right, so those are the 2 criteria that have to be met. So let's look at an example to see how this all works. So we have the overall reaction. Hydrogen reacts with iodo chloride. That forms 2 moles of hydrogen chloride, and we have iodine formed, diatomic iodine. The rate law that has been determined experimentally is equal to K times the concentration of the hydrogen first order and the concentration of the iodo chloride first order. So then they're going to present 4 mechanisms, and you got to figure out which one of these mechanisms is the correct or most plausible. I should say that. We don't know it's correct. All we're going to do is plausibility here. Correct is a different standard. So which one's the most plausible? So the first step says that 2 of those iodo chlorides have to slam into each other, and when they do that, they form iodine and chlorine, diatomic. It's the slow step. And then the chlorine reacts with the hydrogen to form 2 moles of hydrogen chloride. So when we add the first step and the second step together, we get the sum, the overall equation, and the overall equation actually looks pretty good, right? You say, "Oh yeah, that fits right in with what we've been talking about." Here's the balanced chemical equation. All right, so let's prove that that's correct. Let's go back, and you see hydrogen reacts with 2 moles of iodine chloride, forms 2 moles of hydrogen chloride, and forms iodine. So we've met one of the criteria. We've got the correct sum. But then if I asked you to write the rate law for this reaction, what would you write? All right, you may want to stop here and try writing it. All right. Let's look at what the rate law is. Notice this is a slow step, and initially we have iodine chloride reacting with itself. So that should be the rate law. Oops, did I skip over one there? Yeah. So for the rate law, we would get this based on the reaction with that. Let's go back again since I messed up there. Based on the reaction that you see here, that this is the slow step, the rate law would focus on this part here, and that's what we see for the rate law. Well, that doesn't match experimentally what we saw. So mechanism 1 is not plausible because it doesn't. It meets criteria 1. It meets the overall reaction, but it does not meet criteria 2. The rate law is incorrect up here. This is no good. So we got to go to another possible choice. So the next choice is, we say the hydrogen slams into the iodine chloride. We form hydrogen iodide and hydrogen chloride. The hydrogen chloride slams into the other iodine chloride, and we form hydrogen iodide and chlorine. And so if we look at the rate law, this is the slow determining step, we would get rate equals K times the concentration of the hydrogen times the concentration of the iodine chloride. And it is first order. It's first here, in the elementary step. Looks good. So the rate law checks off. It meets criteria 2. But when we add these two reactions together, oh, this isn't right. This is supposed to be I2 in the original equation. It's I2. All right, let's just prove that. Make sure we refresh our minds here. So if you go here, you see that the product is I2, not Cl2. So that kills mechanism 2. Mechanism 2, not plausible. All right, let's look at mechanism 3. So mechanism 3, well, that's problematic in that the rate law would equal that. That's definitely not correct. So mechanism 3, we don't even get out of the gates on mechanism 3. All right, mechanism 3, another thing, I mean, it doesn't sum up to this. So 3 is just nowhere near the correct answer. So let's look at 4. All right, so the hydrogen slams into the iodine chloride, forms hydrogen chloride and hydrogen iodide, and then the hydrogen iodide slams into the iodine chloride, we form hydrogen chloride and iodine, diatomic iodine. All right, so this is the slow step. Yeah, that looks like the rate law. That rate law is correct. All right. So that's criteria 2. The other one is, when we add these two together, do we get the overall reaction? Yeah, that's the overall reaction that we saw before when we looked at the. Let's just go back again to prove it. All right, so there's our overall reaction. That's got to be met, and the rate law has to be met. And let's just go back one more slide to make sure we can speak the language. So for this, they're saying criteria 1 is that When we add up the elementary steps, they have to equal the overall reaction. That's criterion 1. And criterion 2 is that the rate laws match. And so when we go back and look at mechanism 4, we get that. So mechanism 4, we don't say it's correct. Let me just stress this again because I even said that. It's plausible. It meets both criteria. So just keep that in mind. It's plausible. It meets both criteria. All right, so let's have you guys try this problem. Let's stop right here. You work this all out, not go into the other pages. See if you can get the correct answer here, and show me which mechanism is the most plausible. Or is this right? It says write the equation for the overall reaction. All right. Identify the intermediates and identify the rate determining step. All right. So let's see if you can do that. All right, welcome back. So let's do this. If I were going to ask you which one of these steps is the slow step, which one would you say? Well, it has to be this one. That's the reactant. That's what we have here. This is a reactant plus monoatomic oxygen. And so it has to be, this is the slow step. And this is the fast step. All right, it says write the equation for the overall reaction. Well, this monoatomic oxygen is an intermediate. It cancels out. So what we end up with for our overall reaction is 2 moles of dinitrogen oxide yields 2 moles of nitrogen. How'd you get that? You got the nitrogen here and the nitrogen here, plus oxygen gas given off. Does that make sense? Yeah, it's balanced. There's a total of 4 moles of nitrogen on the reactant side, 2 moles of oxygen. We have the same thing on the product side. All right, so we've done that. We did this step. We said oxygen was the intermediate, wasn't present initially, not present at the end. Step 1's the rate determining step. We said that's the slow step, and that's what you would write. That's an easy thing. I think you can do these if you keep the criteria in mind, and you know how to balance chemical equation, and you know that the rate law is based on the reactants, and the slow step determines the rate law. All right, so this is the problem that gives students the most difficulty. So let's look at this one. So it says, sometimes we encounter a reaction with an experimentally determined rate law that suggests an unlikely scenario. So again, not likely to happen. But here we go. We got nitric oxide reacts with chlorine to form nitrosyl chloride. That's what this NOCl is here. So you write the rate law. If this was an elementary step, you know, that looks good, right? Because this is reflects this. So this is what the rate law is determined to be experimentally. And overall, this is a third order reaction. If you add up this order plus the one here, it's third order overall. All right, but we know that that's probably not an elementary step. There's too much going on there. Right here it says, when you have three atoms collide together to make a product, it's unlikely. So we got to think about a mechanism here. So here's the mechanism. The first thing that happens is the nitric oxide slams into the chlorine, forms this intermediate, and then this intermediate's consumed with some more nitric oxide, and then we form the nitrosyl chloride. And notice this is the slow step and this is the fast step. So when you write if this is a slow step, this is the rate law that you would get, right? I think you guys can do that at this point. But here's the problem. Where did this come from? Well, it's an intermediate. So if it's an intermediate in the rate law, then we're going to have to trace that back to where it came from. So this came from this reaction here. And so what we're going to do is we're going to substitute in this for that. And you say, what does that look like? Okay, well, let's continue on. So here we go. The rate of this forward reaction looks like so. Makes sense. That's the rate law, right? The rate of the reverse reaction looks like that. So we set these two things equal to each other. So the rate of the forward reaction, K1, rate of the reverse reaction, K to the -1. We set those equal to each other, and we get this relationship. We substitute in for the intermediate this. All right, so we combine all that together. Now we have all three rate constants. And then we have this times what we originally had. And that gives us nitric oxide to the second order and chlorine to the first order. So I want you to be able to do that. Let's look at this one more time because this is the hardest thing in this section. Here's my balanced chemical equation. Nitric oxide, let's look at it. Yeah, let's go one step back. Is it one more step back there? Yeah. Yeah. Let's go back to this again. Let's talk through it one more time. This is the overall equation. This is not an elementary step. Why isn't it an elementary step? Because you know bonds are going to have to break. New bonds are going to have to form 2 moles of this. We determine experimentally that the rate is equal to K, the rate constant, times the nitric oxide square to the second power and chlorine to the first power. And you go, oh, that looks just like that. Oh, that's great. But you know that's not an elementary step. It's too complex. So then what you have to do is you got to propose 2 steps. So the first step is this, and they tell you that it's fast, which is kind of strange because usually the first step is slow. So this stuff is made really quickly. This nitrogen oxide dichloride, all right? This is an intermediate, and it reacts with more nitric oxide to form 2 moles of nitrosyl chloride. So the slow step is the rate determining step. So you write that for the rate law, and you go, that's not matching the experimental rate law. That's right, doesn't match the experimental rate law. And you notice that this substance is an intermediate. Where did this substance come from? It came from this substance. So what we have is we have to look at the forward reaction here and the reverse reaction. And so we look at the next slide, which is the more complicated one. Yeah, let's just go and skip that. So the forward reaction is this, for this, the fast step, and the reverse reaction is that. We assume the rates are the same, forward and reverse. That's how we're able to set this equal to that. And we solve for the intermediate. We solve for this, and we get this. And then we substitute all of that into the intermediate, and we get this. And you notice that when we do that, we get the rate law that was determined experimentally. So the main thing to remember here is when you have a fast reaction, creates an intermediate, and then you're going to have to substitute the reverse reaction of the intermediate into the concentration of whatever the intermediate is, combine all the rate constants here to get the overall rate of the reaction. All right, so if you understand that, here's your test. Can you do this problem? If you can do this problem and you get the correct answer, you're ready for the exam on chapter 14 other than catalyst. I mean, really, there's not, catalyst is the easy part. This is the more difficult part. So here you go. Here's the overall equation. Here's the fast reaction. Here's the slow reaction. Here's what they tell you that the rate law is. That's the rate law, experimentally determined. So what's going on down here that's going to give us that rate law? So the rate of the forward reaction for the fast reaction is this. The rate of the reverse reaction is that. We know that the rate law for this would be rate equals the rate constant times the dinitrogen dioxide times oxygen. That doesn't match this up here. So we know we got a problem. This is an intermediate. We see it's an intermediate. It wasn't at the beginning, wasn't at the end. So I want to solve for this intermediate. I want to set these two, the rates are going to be the same. We're going to set those two things equal to each other. And we're going to solve for the dinitrogen dioxide. All right, that's what we did right here. We solve for the dinitrogen dioxide. We substitute in for that, all of that into our rate law. All right. And we find out we do get the rate law that they said it should be. And just remember, you have to combine all of those rate constants into one constant. They're not hard. I don't think they're hard. In fact, I think it's like a puzzle. And once you understand that, you're going to do fine. But again, what happens based on the knowledge you know the slow step is the rate determining step. You know how to write the rate law for the slow step. And then you realize, hey, this is an intermediate. Where does it come from? Well, it comes from the fast step. And I need to look at both the forward and reverse reaction of the fast step. And I'm going to set those equal to each other. And then I'm going to solve for the intermediate and substitute that into my rate law. And that will come up with the rate law what we determined experimentally. And then if you have to do a problem with this, you just remember you have to combine all those rate constants. You have to multiply the 2 and divide by the 1 to get the overall rate constant. I hope that helps. I think it's not really difficult. I think some of the math in the beginning of this chapter is much more difficult than this. You just got to follow the breadcrumbs, though. Follow it and know the criteria. Elementary steps add up to be the overall, and so if it doesn't add up to be the overall balanced equation, you've got a problem, and the rate law has to reflect the slow or the rate determining step. All right, last section, pretty easy. A catalyst. What a catalyst does, it generally it lowers the activation energy, and it's not. So it increase by lowering the activation energy, it increases the rate of the chemical reaction, both forward and reverse, though. So let me just kind of draw a picture, and I'll probably show it on one of these slides here. But here's the reactants. You come over the hump here, and then you're at the products. And we know that from here up to the top of this peak is the activation energy. All right, activation energy. A catalyst helps the reaction along, so the activation energy is decreased. It's a little exaggerated maybe, but the activation energy has been decreased that amount. So it's easier for the reactants to get over the hump and make the products. But here's the thing to remember. It also makes it easier for the products, if it's a reversible reaction, to get over the hump and come back and form the reactants. So a catalyst affects both the forward and the reverse of the reaction if it's reversible. So a catalyst may react to form an intermediate, but then it's regenerated in a subsequent step. So that's why we say a catalyst is not created or consumed. Oh, let's say it that way. The catalyst is not consumed in the chemical reaction. cannot be consumed. So again, they just did what I did, but they broke it down into 2 steps. Here is when you don't have a catalyst. Here's when you have a catalyst. The activation energy is lower, makes it easier at a particular temperature for A and B to get over to form C and D. But it also makes the reverse reaction easier too. So generally what a catalyst does is it helps orientation in some way. So here's what's going on here. We have a heterogeneous catalyst. What does that mean? Well, it means one thing is in one phase. Here we got 2 gas molecules, and then we have a solid phase down here. These gas molecules slam into this solid face, and it causes the bonds to break between the oxygen and the nitrogen. And then the nitrogens combine and the oxygens combine, and where we started with nitric oxide, we end up with nitrogen and oxygen. Does anybody know where you would see this reaction? If you know where we would see this reaction, you're in great shape. You understand? You know, I'm starting to say maybe you want to major in chemistry. This is what your catalytic converter does. So SOx and NOx is what we say. SOx and NOx, where the oxygen is a certain number here, 1, 2, whatever. We know that these are pollutants from cars, and so we have a catalytic converter that breaks this back down into nitrogen and oxygen. It's not consumed. That's why your catalytic converter is good for the life of the car unless you somehow poison it. Poisonous where you add some other substance that locks onto the surface and it doesn't escape, and then these things can't collide and stick to the catalyst. You say, when does that happen? If you ever put leaded gasoline in an unleaded car, you're going to run into these types of problems. So there's your real world example. Do not put leaded gasoline in an unleaded required car, otherwise you could damage the catalyst. Homogeneous catalyst, this is probably what you actually see more of than anything in everyday life. You guys maybe have gone to the store, you need to glue something together, and there's this thing that's got like 2 plungers, and then there's 2 tubes. They call it epoxy, and then it combines down here into one opening, and they tell you to squeeze this out onto a piece of cardboard and stir it up, and then they tell you how long it's going to be before it sets. One of these things contains a catalyst which speeds up the reaction. So as long as the catalyst is in there, it may take days for this glue to harden up. But because the catalyst is in on the other side, when you mix these together, you have a certain time frame before they become hard. So those are epoxy type glues or resins. So I know most of you probably have seen that. You've seen it you probably used it even. I'm not talking about super glue. I'm talking about 2 tubes of something together. Sometimes they're actually separate tubes. I've seen them like that, like you get a little metal tube of some substance and another metal tube of another, and when you mix them together and on a piece of cardboard or something, then you can use that to glue with. So homogeneous means same phase. They're both liquids. Both liquids. That's easy to remember. Both gases. They're both the same phase. It can be both gases, both liquids, both solids. I can't think of a solid catalyst, but there may be one. And then heterogeneous means they're separate. All right, so heterogeneous catalyst. What we have here is in the presence of an acid, this substance reacts with water and forms acetic acid and ethanol. Is that ethanol? I guess it is. And so that acid lowers the activation energy. And so the reaction, here's what the rate looks like for this reaction. And here's what the rate looks like without the catalyst. So that's what we're looking at here. And one of those is aqueous, and one of those is this must be, I don't know, that it might be explained in the book. I mean, it says heterogeneous, so that means there are two different phases here, and I don't have the book open to explain which one is what's going on there. So enzymes are biological catalysts, and they can increase biochemical reactions by factors 10 to the 6, 10 to the 18. They're highly specific, and I do want you to know that if you're a biologist, you need to really focus on this part. The enzyme acts only on certain reactant molecules, all right? That's called substrates, while leaving the rest of the system unaffected. Enzyme catalysis is usually homogeneous because the substrate and the enzyme are both present in aqueous solution. And I think that's what's going. Let's go back to this one. I'm going to take a guess. I haven't read this but I assume this is aqueous, this is a liquid, a pure liquid, and that would make it different phases. All right, so here's how it works. You have the enzyme, you have the substrate, and the enzyme locks in with the substrate, and then that enzyme is released, and then we have our new substance here. All right, so this is an intermediate. It wasn't present initially, wasn't present at the end, and the enzyme is not consumed in the reaction, but S is converted to P. All right. Now, if there's not enough enzyme there, we can get a here's a good picture of it. All right, so here's your enzyme, here's your substrate. Notice it's very specific. It locks only in at this place. We get the enzyme substrate complex. The bond breaks here in the substrate, and we get two different products now, and the enzyme is released, ready to use again. What's really interesting about this, let's think about digestion of food. You don't want to eat food and it all break down into the product directly. If you did, your body temperature would go through the roof. You know that when new substances are formed, that new bonds are formed, energy is released, and if all that energy is released at one time, you'd actually see your body temperature shoot through the roof. So there's only so many enzymes in the stomach that can break down this substance, this substrate. So once they're all used up, or once they're all being used, then there's no more of these to react with, and that slows down the process. So and these enzymes can be inhibitors as well as catalysts. So just keep that in mind. Keep that in mind that, you know, maybe it's a good thing that it's very specific, because, again, you don't want all your food to rapidly break down and form new compounds and raise your body temperature. So, again, this is just showing here's what the reaction would look like going from S to P. But here we're forming with the substrate and the enzyme, we get an enzyme substrate intermediate, and then we end up with P. And E is regenerated for another reaction. Use this a lot in biology. And then we can calculate this out. I'm not asking you to do that, so I don't think that's in our homework at all. We'll skip that part. Here's what I was talking about. All active sites are occupied. Then you can't have any more reaction. So it can be an inhibitor as well. That's an important slide there. All right, that stops chapter 14. We're finished with kinetics. I'm hoping you're watching these in little sections, and I know these are long videos, and I don't intend for you to sit down and listen to this for 40 minutes or whatever. It's a little at a time. Hopefully you're reading the book and you go, oh, I don't know what's quite going on here. You can watch a section of this and figure out what's going on. So I hope that helps.